My people, I hope we're doing well today. What we're going to start on here is we're going to run through some trig, trig integration, and largely what these are is they are basically a collection of different methods whereby we need to make use of our knowledge of trig identities in order to change the form and arrive at appropriate integrals of trig functions, right? Or combinations of trig functions. But in order to start us out, what I think it's important to do is to show you the integral of the four trig functions beyond sine and cosine. Because sine and cosine are relatively easy to anti-differentiate or to integrate. The derivative of sine is cosine, so the integral or the antiderivative of cosine is sine x plus c. And similarly for cosine. But when you get into the other four trig functions, you need to remember that their derivatives are of the second degree, okay? And because their derivatives are of the second degree, secant by itself is not a recognizable derivative, and therefore it cannot be integrated from this particular form. Now on these, especially the secant and the cosecant, you don't need to be able to recreate this. You simply need to be able to understand what it is that I'm doing, okay? And then just sort of remember it from there. Secant, and this is sort of one of those clever ways of changing the form by multiplying by 1 in a creative way. What we're going to do is we're going to multiply by secant plus tangent over, and I'm going to go ahead and turn it around, and the reason will be apparent here in just a moment. But despite the fact that, the denominator is in a different order than the numerator, by the commutative property of addition, we know that the numerator, denominator, they're equal, so that ratio is equal to 1. So when multiplying secant by this ratio, I have not changed the value of the integrand. I have merely chosen the form. Okay, so I've changed the form, not chosen, changed the form, and basically what I need to do is I simply need to distribute that secant. So I get secant squared x plus secant x tangent x, all of that over tangent x plus secant x. Now the reason why I reversed the denominator was so that these were right on top of each other. And you notice that the derivative of the denominator is, the denominator is two terms. The derivative of the denominator will be two terms. And the derivative of tangent is secant squared, and the derivative of secant is secant tangent. And therefore, what we have here, if you were to do a u sub, is you have the denominator as your u and the numerator, if you sort of fold in this differential right here, being your du. And therefore, basically, we integrate by using natural log, and all I had to do was simply know to multiply by that quantity right there. So it's natural log, absolute value of tangent x plus secant x, and of course it could be natural log secant x plus tangent x, it doesn't really matter, plus c, and that is the integral for secant. Now tangent winds up being a little bit easier because when you turn it into its implied ratio, it already is set up it's almost set up to do natural log just straight from there. The only thing you need to remember is that for the numerator to be the derivative of the denominator, it needs to be negative sign, which means I pop a negative out in front here so that I've multiplied by -1 twice, and therefore I've multiplied by 1. And this becomes negative natural log absolute value of cosine x plus c. Now, sometimes it's written like this. I find that negative out there to be annoying, and since when it comes to careless errors, I was always the person to lose the negative, I actually prefer it in this form because by properties of logarithms, I can pop that negative up and have it be natural log of cosine x to the negative 1, which basically just asks you to take the reciprocal of cosine, which, as we all know, is secant. So I prefer this form. If you want, you're welcome to do it in that form. It matters not to me. Now, we can probably proceed a little bit more quickly with cosecant and cotangent, largely because they basically wind up having the same trick as their cofunctions do. But we got to be careful, because anytime you're dealing with cofunctions, you're dealing with those negatives, right? We recognize the fact that when we're taking the derivatives, the derivative of sine was cosine, but the derivative of cosine was negative sine, and the derivative of cosecant was negative cosecant cotangent, and the derivative of cotangent was negative cosecant squared. So that negative obviously comes into the fray when we want to undo that differentiation, so we have to be careful there as well. But we're going to start out the same way that we did with secant, by putting cosecant over 1 and then multiplying it by something. Now, what I want to do, obviously, is I want to multiply by cosecant x plus cotangent x over cotangent x plus cosecant x. But I have a problem, because I know that my numerator is going to need to be the negatives. So, because the derivative of cotangent, and you can do the negatives here, but let's actually wait until the next step so we can actually see it a little bit better. Now that I've multiplied by 1 in this form, right, and I did exactly the same thing I did with secant and tangent, I just reversed the order of the denominator so that the derivative would line up right over what it is the derivative of, and we get cosecant squared x plus cosecant x cotangent x, all of that over cotangent x plus cosecant x, and that is almost perfect, but remember that both of these need to be negative. So again, if I'm just like I did with the integral of tangent, I made the numerator negative. I just have to do the same thing here. It just so happens that I have to distribute it across both of these terms and then put a negative out in front to basically compensate for that. Now, that means that I'm going to get negative natural log absolute value of cotangent x plus cosecant x plus c. And there are numerous ways to actually change the form of that. If you just want to memorize it in that form, that's just fine. But remember that cosecant and cotangent have the same denominator. Okay? They both have a denominator of sine. This is cosine over sine, and this is 1 over sine. So you actually can turn it into a single rational expression and then use that negative 1 to change the form of it. Okay, so if you wanted to, it could become negative natural log, and like I said, cotangent is cosine over sine, so it would be cosine x plus 1 over sine x plus c, and then we could turn it over. But I don't really like turning it over, because then I have a denominator that's a binomial. But you also got to remember way back to verification of trig IDs and analytic trig, that you can actually change this denominator by multiplying it by 1 minus cosine over 1 minus cosine, and therefore you can get the natural log of 1 minus cosine over sine plus c. So, I mean, there's a veritable cornucopia of ways that you can actually change the form of that one. And if you want to memorize it in one of those forms rather than all of those forms, but I'm just trying to show you that there are several ways to do it. I would want to memorize it in this form, largely because I don't have a negative out in front, and that expression has a monomial denominator, and I just have this bias towards always trying to make sure that I can change things into a monomial denominator and do so when I can. All right, let's move on to cotangent. Cotangent actually winds up being easier than tangent because I don't have to change anything, right? The denominator is sine, the numerator is cosine. I don't have to negativize cosine in order to make it the derivative of the denominator, which is sine. It already is. And so this is already in the form of du over u, and therefore what I have here is the natural log of sine x plus c. Okay, so those are the four those are the ways of getting the integral of the other four. Okay, and when it comes to several of them, there are several different forms. You can keep them however, you can basically put it however you want. But just make sure that if you're going to, when you memorize it, you're memorizing it in the most useful way for you. Okay. Now, once we get beyond simply laying out the integrals of these last four trig functions, what we're going to be doing, which of course is one of the things that's consistent throughout this chapter, and one of the things that's just consistent about mathematics in general, but we're going to be bringing to bear several of our techniques for changing the form of things such that things that are not integrable in the form that they are given can be transformed into something that is integrable. And of course, in the last thing, we actually use the product rule to basically substitute an expression that was integrable for one that wasn't, by means of the product rule and stuff like that. And that was really neat. But what we're really going to be concentrating on in this particular one is we're going to be concentrating on the trig IDs. Okay? And the trig IDs, you should remember these. These are the ones that are going to be most common for our purposes, and largely, usually it winds up being really, really helpful. These wind up being really helpful. You don't oftentimes get an integral that has sine squared plus cosine squared in the integrand. For the rest of these, it's going to be it's not going to be the one with both on the same side. It's going to be the one where you're basically trading one trig function for the other. Down here on the double angle identities, this one is always real easy to use and real fun, but these of course are going to become really, really helpful as well. The tangent one doesn't come in all that often, but it could. Now remember that we talked about in class how especially the double angle identities for cosine are the jumping off point for us to actually find the rest of the trig IDs. Now the rest of the trig IDs are ones that oftentimes are not, the pre-cal students are not required to memorize them. These three, however, are going to be extremely helpful. And you'll see why. We discussed it a little bit in class, but you'll see further why as we move forward. The half angle identities, not so much, but if these are useful, you can always use the double angle identity in order to derive these. Because also notice that basically there is a kinship between this and this. All I have to do is call u over 2, and call 2u, u, and then just take the square root of both sides. So there is that kinship between these two. These down here are always the nasty ones, the sum to product and the product to sum. These right here can be useful. It's up to you whether you want to memorize them or not. I don't think that they're used often enough to be worth memorizing, but make that call on your own. But the whole point of this is using trig IDs to change the form. Now, oftentimes that is in conjunction with one of the other methods that we've already learned, whether it be u sub or parts, and we'll talk about that as we move forward. But let's go ahead and jump into a couple of examples. Let's start with some easy ones. That means we're going to start with sine and cosine. Now remember, like I said, what we're going to be doing is we're going to be using our trig IDs to change the form such that I can then use another method. And oftentimes on ones like this, it's going to be u sub. So if I'm going to change the form, in anticipation of using U substitution, I need to keep in mind that when I'm changing the form, I am functionally making decisions about what my U is and what I want my du to be as well. So on this one, notice that we have a sine to an odd power and a cosine to an even power. Now, if I'm going to be using Pythagoreans in order to change sine into cosine or cosine into sine, I need to remember that basically that helps me get rid of or transform or change the form of an even number, right? Using Pythagoreans, there's no way to get rid of all three of these sine functions. I can only get rid of 2, 4, 6, or 8 using Pythagoreans, okay? Likewise, with this cosine, I can get rid of all 2 of them. Now, but what we need to remember is that when I'm changing sine into cosine, I'm functionally saying I want my U value to be cosine. If I'm changing cosines into sine, I'm choosing sine as my U value. But when you do that, you need to remember that if you're choosing sine as your U value, there needs to be a cosine left behind in order to create your du. And we did an example like this in class. If I were to actually choose sine as my U value, that means that I'm going to change that cosine by means of Pythagorean into 1 minus sine squared. And then, of course, I can go ahead and distribute, and I get sine cubed minus sine to the 5th x dx. Now, it's all in terms of one trig function now. And here's the problem. If I say u is equal to sine x, my problem is that I need a cosine x left in that integrand in order to create my du, but I haven't left myself that. Which is why if you have sine and cosine, the one that's odd is going to form your du, because it's going to be the one that after you perform however many Pythagorean identity replacements you need, it's going to be the one that has the leftover in order to pair up with the dx. So if I were instead to choose cosine as my u, I'm going to change the order a little bit here. Let's go ahead and put that cosine squared that was in the original integrand up front. Let's take 2 of those and turn it into 1 minus cosine squared. And then I have left sine x dx. Well, that's going to be a little bit better because I have cosine squared u minus cosine to the 4th, x. And that helps me because I now know that my u is going to be cosine x and my du is going to be negative sine x dx. And the only thing standing between me and a du is a numerical factor. Well, that's taken care of easily enough. You plot the negative in there, put a negative out here, or alternatively, you could use that negative to flip this difference, and that puts everything in descending order. Whatever you want to do. I would actually prefer to do that. So let's actually, turn that positive, and let's flip this difference. And that means that our answer is going to be nice and tidy and in descending order. So basically what happens here is I get u to the 4th minus u squared du, and therefore my final answer is 1/5 cosine to the 5th x minus 1/3 cosine cubed x plus c. And it's all about changing the form in a way that leaves you that residual trig function, or when we get to secant and tangent and cosecant and cotangent, more than one, that actually pairs up with the dx to create your du. And of course the logic runs exactly the opposite way when cosine is raised to an odd degree. When cosine is raised to an odd degree, that is going to allow me to transform an even number of them, in this case 2 of them, and that's going to leave me with a cosine x dx, such that I'm going to have sine to the 4th x minus sine to the 6th x cosine x dx. My u in this case is sine x. My du is cosine x dx. And I have that, right? I have my du right here, and I have my u to the 4th minus u to the 6th right here. Now you can actually transform it into your u's if you want, or you can just know that that's what you're doing, and that becomes 1/5 sine to the 5th x minus 1/7 sine to the 7th x plus c. Okay, and all that basically to say is that this strategy did not work out because it didn't leave behind something that allowed you to create a usable du such that you could do the trig substitution. I hope that is helpful. We're going to go ahead and call this first video to a close, and we'll continue to do more examples in the succeeding videos. I don't know how many videos it's going to take. It depends upon, how often I go off on these little explanatory rabbit trails and how often I choose to work things in multiple ways. But I'll continue to work problems until I feel that I've made a sufficient number of videos. If you have any questions, please do shoot me an email. Bye.